evening, everyone. This is our third day of faculty development program on advancements in IoT and AI for smart cities, green mobility, and SDG-driven urban transformation. This faculty development program was sponsored by AICTE Atal. Today, we are going to have two sessions. Our first session resource person is Dr. M.M. Rajan Singarwal, who earned his BE and ME and PhD from NIT Trichy and is Assistant Professor, Electrical and Electronics Engineering, NIT Puducherry. His areas of expertise are hybrid wind, PV energy systems, power electronics, renewable energy, and smart grids. He received the SIR Early Career Research Award and has worked on projects with DST and ISRO. Sir, we welcome you to the session.
Thank you. Thanks for your nice intro. So first of all, I would like to thank the Institute for organizing such a wonderful workshop with the title related to IoT, smart cities, AI, which is a need of the hour. And so I extend my thanks to the Department of Electrical and Electronics Engineering, HOD, and other coordinators for considering me to offer one session in this Atal sponsored FDP. So with this, let us go to the topic. So today's topic, let me share the screen and you let me know whether it is. The screen is visible?
Yes, sir, it's visible.
Yes. Okay, right. So the title of this particular session is going to be Optimal Sizing of Hybrid Renewable Energy Systems for Net Zero Energy Buildings. When we talk about smart grid, smart cities, then the sustainability comes into picture. And this net zero energy building and net zero energy concept are gaining more attention across the world as it is going to be an integral part of our society in the near future. So this net zero energy, and we all know that the electric energy demand is keep on increasing because of the population and the urbanization, industrialization. Many reasons are there, which is increasing or elevating the energy demand every day. And among them, the industrial sector is definitely one of the major consumer. And apart from that, the normal domestic customers like us, they are also holding a major share in the electricity consumption, particularly the residential buildings. So this graphs can, from this graph, we can understand how the electricity consumption has increased from 1950 to 2019. So we can see the drastic increment in the consumption. The reason is population, industrialization, and many other technological development. So we are in a position to satisfy ever increasing electrical energy demand. And out of the total electricity consumption globally, 40% of the electricity consumption is from the building in the sense of domestic buildings. In India, out of the total electricity consumption, 33% of the share is with the building's electricity consumption. And these are all the data from the International Energy Agency. And even though we can generate the required energy and power from the centralized generating stations like NLC, Kudambalam power plant or Kalpakkam power plant, we can generate power. But with the existing grid infrastructure, transferring such huge power to the consumer end is always a difficult task or a challenging task. So consumers are encouraged to move with renewable energy sources on their own site, to attain the goal of zero energy building. It means that every building should have on-site renewable energy generation to meet its demand. In case, if a building can generate renewable power, renewable energy equal to its consumption over a period of a year, then we can say that particular building is net zero energy building. A building which is having its own renewable energy generation, and if it can generate an amount of energy which is equal to its own energy consumption over a period of 365 days or 1 year, then we can say that the building is net zero energy building. Every instant, the generation and the building demand cannot be made equal. Sometimes generation will be higher than the demand. Energy will be given to the grid. Sometimes the generation will be much lower than the demand. So we will import energy from the grid. So, but at the end of 1 year, the total amount of energy generated by the renewable energy system, if it is equal to the total energy consumption of the building, then we can comfortably say that the building is net zero energy building. And there are many definitions for the zero net energy or net zero energy available in many literature. Few are listed here. First one is net zero net site energy use. In this type, the amount of energy provided by on-site renewable energy source, if it is equal to the amount of energy used by the building, then we say that it is net zero energy building. Generally, this is the statement used in United States. Next one, zero net source energy. This one is a little bit different. This zero net energy generates the same amount of energy as is used, including the energy used to transport the energy to the building, not only the energy consumed by the building. So how much energy is lost in transporting the energy from the generating station to the building? That also will be accounted for the calculation of net zero energy. If you calculate that, then we call it as zero net source energy. And some countries follow this definition to identify the net zero energy buildings. And we have something called net zero energy emissions. Then it is defined as a building with a zero net energy emission, and it is also known as zero carbon building or zero emission building. Right? Under this definition, carbon emission generated from the on-site or off-site fuel use are balanced by the amount of on-site renewable energy production. In that case, we call that building a zero emission building or zero carbon building, something like that. The next one is net zero cost. In this definition, the cost of purchasing energy is balanced by income from the sales of electricity to the grid, which is generated on site. This is not equating the energy produced. This is trying to balance the cost of energy used and the cost of energy sold to the grid. If both are equal, then we say it is net zero cost building. So similarly, we have so many definitions for this net zero energy. But what we are going to take here is, if a building is able to generate an equal amount of energy to its consumption or higher energy than the consumption, then we call it as net zero energy building. So we are going to take this definition and we are going to work on this, or we are going to investigate some features of this net zero energy building, particularly how to decide the size of a renewable energy plant. It may be a solar, it may be a wind, or it may be a hybrid wind PV, or it may be having a hybrid source along with a battery, right? How to size these components? How for a particular building, how much PV, how much wind, how much battery is required? What is the best way to decide that? That concept we will be discussing in this particular session. So we have many renewable energy sources. We know solar, hydro, wind, tidal, thermal, biomass, each are having their own advantage and disadvantage. And but the hybridization will give us a better reliability. It means that when we combine more than one renewable energy sources for a particular site, the reliability of that particular system increases. The reason is, any renewable energy source is unpredictable. We cannot predict anything regarding the renewable energy source. Suddenly, we may not get any solar irradiation for 2 days or 3 days. Then all our prediction will be failed. Similarly, there won't be enough wind for continuously for 1 week. Then all our prediction and estimation will be in vain. So this is always a threatening factor with respect to the renewable energy sources. But when we combine or hybridize more than one source, there is a chance to get power from one source, even if other source fails to supply. So in that case, in that aspect, we can combine any of the source: solar hydro, solar wind, solar tidal, geothermal wind, biomass and hydro. We can have any combination. Among all these combinations, solar and wind are widely accepted across the world. Reason: solar and wind are it is available across the world without any geographical problems or restriction. Second major thing is complementary in nature. They are complementary in nature. It means that over a period of time, whenever the solar power is less, we can witness a high power output or high yield from the wind energy system. Similarly, whenever wind energy is low, we can expect a better energy generation or power production from solar PV. So in that way, the variability is reduced, uncertainty is minimized because the sources are complementary in nature. So we are going to consider a hybrid wind solar generating station for a particular building. Along with that, we are going to incorporate battery storage systems also. So now the task is how to decide the capacity of solar PV, how to decide the capacity of wind turbine, and along with the battery storage, how much capacity of battery should be chosen. The ultimate aim is we need to construct a net zero energy building. And to achieve that net zero energy building, what capacity of solar, wind, and battery should be chosen? What are all the methods that have been already used, and what are all the drawbacks, and how can we overcome that? Right, this is the advantage of hybridization, which I mentioned, because this hybridization, regarding this hybridization, our Ministry of New and Renewable Energy in 2018 itself, they released a policy called National Wind Solar Hybrid Policy. After a thorough research across the country, they identified potential sites where hybridization of solar and wind can be incorporated to minimize the variability and uncertainty. So that also the interested researchers and faculty members can refer that particular orders. So the task of the work is we need to minimize the cost of the system by choosing minimum capacity of PV, wind, and battery. But at the same time, that capacity of wind, PV, and battery should meet the load demand. That is the second objective. Not only meeting the load demand, at the end of the year, the building should be a net zero energy building. So whatever the capacity that we decide or choose, that should be able to produce energy equal to the consumption of the building. So net zero energy should be met. But now, these three are mandatory for any net zero energy building. Apart from that, we have two more additional objectives here that makes this procedure very unique when compared to the other procedure. The rest two are, we need to reduce the grid burden. What is meant by grid burden? How to reduce it? Second one, to improve the reliability. Reliability is also a very common task, but the fourth point, we need to reduce the grid burden, which means when we integrate any renewable energy systems to the grid, the uncertainty or variability in the power production or the energy generation from that particular renewable energy source, that will definitely impose many drawbacks on the grid. Because at any point of time, the grid should have a balance between the generation and the demand. When penetration of renewable energy is more, and if it is highly variable, then there may be a problem in maintaining this balance. So sudden power injection, energy import, energy export to the grid, or sudden energy import from the grid, all these are leading to further consequences, and obviously all these are categorized as a grid burden. So the capacity of PV wind battery, that should be optimally sized, that it will not burden the grid. It means whatever the variability that happens in the wind, solar and battery, that should not have a great burden on the grid. There should not be any major deviation in the power balance of the existing grid network. That also should be satisfied. This particular task, this particular objective was not considered by many researchers so far, and that has been considered in this work, and that's why I mentioned that this particular objective makes this work very unique. And how did this work address this issue? Let us see that. So from the literature, what has been inferred is installation cost of solar PV still remains as an expensive one. And when we talk about reliability, I mean, I have to get in net zero energy building, no option. It means by oversizing the PV and the wind, we can easily achieve net zero energy. There is no doubt. Because what is net zero energy? The energy generated by the system, renewable energy system, should be equal or more than the energy consumption of that building. So without any rigorous iteration or optimization, if we simply install higher capacity of wind, PV and battery, then definitely that is going to generate more energy than the actual consumption of the building. Then the building will automatically will be considered as net zero energy building. But that is the main reason for all grid burden related issues, right? So this renewable energy sources should be optimally designed to exactly meet the load demand, and also to minimize the unwanted energy export and the import. Unwanted energy export and the import. Let us give you an example. What, as per the definition, if a building is considered as a net zero energy building, but as I mentioned already, every instant the building energy cannot be exactly met by the renewable energy system. Sometimes renewable energy system will generate more power than the building demand. So during that situation, the excess energy will be exported to the grid. And on the other conditions, generation will be lesser than the demand, so that deficit energy, the remaining demand, will be met by importing energy from the grid. So this energy import and export is unavoidable, right? So for example, this is unavoidable. We cannot have zero import and export. It means that reliability is 100%, right? We have some results like that, but practically it is difficult. So there will be always some energy export and some energy import. Let us say one building is having, we have two buildings, identical buildings. Consider we have two identical buildings, and one building is having some capacity of PV, wind and battery. It is exporting 10 megawatt hour and importing 10 megawatt hour. Consider it is exporting 10 megawatt hour, importing 5 megawatt hour. Consider it is 5 megawatt hour over a period of 1 year. It has exported 10 megawatt hour, imported 5 megawatt hour. Right? It has reached the net zero energy constraint. It was satisfied. But during this 1 year period, as a cumulative, it has exported 10 megawatt hour. During the deficit energy condition, it has imported 5 megawatt hour. So the total energy transfer is 10 megawatt hour export and 5 megawatt hour import. So totally 15 megawatt hour power transfer happened between the building and the grid. 10 megawatt hour on one direction, 5 megawatt hour on the other direction. But without the sign, if you see the quantitative analysis, it is 15 megawatt hour energy transaction has happened between the building and the grid. Now let us go to the next similar building where some other engineer has designed the PV, wind and battery. It is also achieving the net zero energy, but it has imported only 5 megawatt hour and imported 3 megawatt hour. So put together, total energy transfer is just 8 megawatt hour. The first building total energy transfer is 15 megawatt hour. Second building energy transfer is just 8 megawatt hour. Both are net zero energy building. Both are having same load pattern is same, everything. So now which one is beneficial? Definitely the second building design is better because it achieves net zero energy building, it achieves reliability. Apart from that, it has reduced the grid burden as well because the energy transaction, unwanted energy transaction between the building and the grid has been reduced by half. It was 15 megawatt hour in the first building. Now we have only 8 megawatt hour, almost 50%. So this unwanted energy transfer, we call it as total energy transfer between the building and the grid. This particular parameter has not been considered for any design so far. So in this work, how to reduce that total energy transfer, that also has been considered in the sizing process, and the results are really promising. We can see the drastic improvement in the result and other parameters like reliability, cost, grid burden. In terms of all these parameters, the proposed method or the method that I am going to discuss now outperforms all other methods which has been discussed so far. So now consider this is a graphical illustration of the net zero energy building. We have solar panel, we have wind, we have battery, and we have the utility grid here. So energy will be exported, energy will be imported. So this total is called as total energy transfer. Now, apart from satisfying the minimum criteria for the net zero energy building, I have to minimize this total energy transfer, right? So this also has been considered as one of the minimization function in the work. So just remember this block diagram. So from the literature, when we investigated the literature, there are many literatures with a single objective function. Mostly the single objective function will deal with the cost, because obviously the investor will worry about the cost of the investment. So they will be trying to minimize the cost. So generally the single objective function will be based on the cost. So only objective will be minimize the cost of the system. That's all. So in that condition, the loss of power supply probability, fluctuation rate, renewable energy factor, inflation factor, many parameters like this are considered as the constraints, right? And as an advance to this, because there is no point in minimizing only the cost. If you minimize the cost, then definitely the reliability becomes a question mark. This reliability and cost both are inversely proportional. Both are contradict objective. Maximizing one objective will minimize the other. So obviously we need to go for multi-objective optimization. So where we will be trying to minimize the cost and minimize the loss of power supply probability for the loss of power supply. So this is also a reliability factor. So both will be minimized. It means that if you try to minimize the probability of power loss, it means that it is increasing the reliability. So both function will be minimized. So this is what we call it as, multi-objective function means trying to minimize two contradict objective. It's called multi-objective function optimization. So cost and LPSP are two different contradict objectives. Now, with this two objective functions, many literatures have proposed many sizing technique, but in any of those literature, this total energy transfer has not been considered. So all those results provide a solution, better solution, not the best solution, a better solution, which has better cost and better LPSP. But when you analyze the total energy transfer, the unwanted energy transfer that took place between the building and the grid is highly, enormously high. Enormously high. All the buildings are achieving net zero energy, but it is having unwanted energy transfer in terms of megawatt hour, kilowatt hour, in terms of 50 kilowatt hour, 101 megawatt hour, something like that. So yeah, all these unwanted energy transfer between the building and the grid leads to grid burden, leads to unwanted transmission loss and efficiency, everything. So this has to be minimized to have the reliable and grid-friendly net zero energy building. So that particular objective is also considered as the third objective function along with the cost and the LPSP. Along with the cost and the LPSP, total energy transfer, an index, is also considered for minimization as the third objective function. So in our work, we are going to have three objective functions to be minimized. One is cost, second one is LPSP, third one is going to be the newly formulated index called total energy transfer index. Cost, LPSP, and total energy transfer. So, so once again, the slides put all the literature in a nutshell. If you undersize the system, your cost will come down, but your reliability becomes a question mark. Whereas if you oversize the system, it increases the energy export. Unwanted energy, excess energy will be exported to the grid, which is a burden. Right? So if you oversize the system, reliability increases, but unwanted energy transfer increases. And total energy transfer will increase on both the condition. Whether it is an undersized system or oversized system, total energy transfer will increase, which leads to the grid burden. So what can be done? We can go for incorporating the storage element like battery. That will reduce the, that will help us to store the surplus energy, and it helps us to reduce the energy export. And it will deliver whenever the renewable energy system is not able to supply the demand. First priority will be getting the power from the battery. Only if the battery power is drained, then the energy will be imported from the grid. So by keeping all these things in mind, to have a better capacity to manage or to have best compromise between cost, LPSP, and the total energy transfer, three objective functions as listed here, cost, LPSP, and TED, should be minimized to meet cost-effective reliability and less grid burden system. So all these sources are modeled here. These are all the basic equations. So let us not spend more time on this. Anyway, you can refer these slides at the end of the once it is already shared, so you can get it from the organizers. So this first thing is, see, this is the PV generation basic PV equation. Second one is basic wind equation. Third one is the basic modeling equation of battery storage. And now we come to the objective functions. Three objective functions. First one is annualized cost of the system. What is the cost of the system per year? It means any renewable energy system will have a capital cost and will have the maintenance cost every year. The life of the renewable system will be for 25 years. So if you average all these capital cost and maintenance cost for the entire lifespan of the system, then we get the annualized cost of the system. Every year we have to spend some amount, something like that. So that is called annualized cost of the system. Second one is reliability, which is the factor called loss of power supply probability. If this loss of power supply probability is 0, which means reliability is 100%. In case loss of power supply probability is 1, then the reliability is 0, right? Both are opposite. Then the last one is the total energy transfer. Total energy transfer. How much energy is transferred between the building and the grid, which means energy exported to the grid and the energy imported from the grid. Both will be added together to calculate the total energy transfer. We should not find the difference, right? Both values should be added together. So this is the equation for annualized cost of the system, which includes the capital cost and the maintenance cost of all the components, main components like PV, wind, and the battery. As far as the battery is concerned, in a lifetime of solar PV and wind, battery will be replaced at least 4 or 5 times, because the lifetime of battery is just 5 years or 4 years. So the replacement cost of the battery also should be considered to calculate the annualized cost of the system. The values considered for this work are given in this table, and the references also mentioned. Next one is reliability. As I told you, this is the loss of power supply probability. So if LPSP is 0, it is called as 100% reliable. System is 100% reliable. If we get LPSP as 1, then it is called 0% reliable. Reliability is 0. The next one is total energy transfer. What is total energy transfer is? Total energy transfer will be calculated only during the 2 conditions. Only when the battery is completely charged. Battery is completely charged, so it is removed from the system. Now we have excess energy during the time. Thus, excess energy will be given to the grid or exported to the grid. It is called as energy export, right? Total energy generation minus load energy, load power for that particular hour will give us the total energy, total power exported for that particular hour. So as it is mentioned for 1 hour, it can be equated to the energy of that particular hour. Similarly, when if the generation is lesser than the demand, first the battery will try to deliver the power to manage the deficit value. Once the battery is also discharged to the lowest level, then the power will be obtained or imported from the grid. That is mentioned as energy import. It will be calculated from the difference between energy generation minus load. But what is the total energy transfer is? We need to add this. We need to add these 2 values irrespective of the sign, right? Even if this energy import becomes minus, because in this condition we'll get, because the energy from PV and wind is lesser than the load demand, then only we have energy import. So this will become minus. I forgot to mention it here. It will become minus. But without taking the minus sign, that value alone should be added with the energy export to get the total energy transfer. So from that, for the entire year, what is the total energy transfer happened? Every year, the total energy transfer has to be calculated here. Then that will be divided by the energy generated by the renewable energy sources. So this will give us a factor called total energy transfer index. It is newly formulated for this work. Now, minimizing this factor, TETI, total energy transfer index, will minimize the unwanted energy transfer which is happening between the building and the grid, and it ensures the minimum grid burden. So the lower value of TETI implies minimum energy transfer, and the higher value implies maximum energy transfer between the building and the grid. So constraints energy generated over a year should be equal or greater than the annual energy. So this is the net zero energy constraints. These 2 are net zero energy constraints. And we should fix some minimum and maximum values for the decision variable. Decision variables are capacity of PV, capacity of wind, and the capacity of battery. So we can fix the minimum and the maximum values of these decision parameter as mentioned here, maximum and the minimum values. Now, first, the PV wind, the BS will be optimally sized using an optimization algorithm called NSGA2, non-dominating sorting genetic algorithm 2. That particular algorithm is used in this work. And this NSGA2 ranks the population based on non-dominated sorting algorithm, but non-dominated sorting, and it will not dominate any one of the solutions because we need to minimize 3 solutions. And as mentioned here, this is a non-dominated algorithm or optimization procedure. So by giving weightages, we cannot get what we wanted. So the algorithm will minimize all the 3 parameters to the best level. The entire flow chart is shown in this particular slide. Each and every step is shown here, whatever we have explained. Right. Anyway, let me explain this once again. So the first, the decision variables are decided. Then NSGA parameters are initialized. For the first iteration, the capacity of wind turbine, PV, power, battery condition, everything will be calculated for every hour. First, it will be calculated for 0th hour, and it will be continued. It will be calculated for every hour. So for the obtained PV, wind capacity, and the load condition, we have to check whether the energy generation is greater than the load demand or lesser than the load demand. Based on that, whether the battery is charging or not or discharging or not, everything will be decided based on this particular condition. And further, if it satisfies the net zero energy balance constraint, then we will calculate the objective functions and all selection, crossover, mutation, and everything will be calculated. Then finally, we will get a set of solution. We call it as Pareto friend. We get a set of solution. All are optimal solutions, but nothing is best. So from the available Pareto friend solution, we need to pick one solution as the optimal solution to design the net zero energy building. Now, in order to demonstrate the effectiveness of the proposed 3 objective function technique, the same work with the same data, it has been tested for normal 2 objective function sizing techniques. The 2 objective function sizing technique will have cost and the LPSP as the 2 objective functions. Whereas in the proposed method, we have one more objective function, which is total energy transfer index. Total energy transfer index. The Pareto friend solution gets generated from energy after 400 iterations. Right. And now, based on this NSGA2 algorithm, based on through the proposed technique and through the conventional technique, algorithms are executed for these 2 conditions, and the results are projected here. Right. The first graph shows the 3 objective function sizing technique solution. As we can see, this is a 3-axis graph. Whereas the second graph shows the 2-dimensional graph because it involves only the minimization of cost and LPSP. So after obtaining the Pareto friend for both methods, 3 objective function sizing, which is the proposed one, and the 2 objective function sizing technique, a conventional one, from the Pareto sets of these two solutions, one solution has to be obtained. One solution has to be obtained. Now, for 100% reliability, what is the solution given by the proposed system and by the conventional system? That particular result has been taken and projected in these two slides. You can see this is the power generation, energy generation of the system using the proposed technique and as well as the conventional technique for a random month in that particular year. Some random, sorry, this is for the entire year, month-wise energy generation. You can see that you can see one bottom pink color line, which is denoted as energy import. In both these cases, there is no energy import at all. What is the reason? These two figures or two cases are drafted for the condition called zero LPSP, which means 100% reliability. The system, the PV and the wind battery, they can satisfy the demand of the building throughout the year. So the LPSP is considered as zero, right? And you can see the yellow color line, that is the energy export. How much energy is exported? And the red color line is the PV power, blue color line is the actual load, and the black color bar is the wind power. You can see the yellow color line, which shows the energy export. Energy import is zero for both the condition, but the energy export is lesser for the three objective function sizing technique when compared to the two objective function sizing technique. It means that if you decide the PV with the battery capacity through the proposed procedure sizing technique, you end up with the minimum energy export. That has many positive consequences. And similarly, we have a energy for a random day, 24 hours. You can see the graph here. And here also this pink color line is the energy export. Yellow color line is the energy import. You can see with the three objective function sizing technique, the peak energy export is around just 15 kilowatt hour. Peak energy export is just 15 kilowatt hour. It has happened to some a fraction of a second or 1 minute or 2 minutes. This for the same condition, if we decide the system with the two objective function sizing technique, the energy export is around 45 kilowatt hour. Here, this is just 15 kilowatt hour. The next is 45 kilowatt hour. From this, it is very evident that the proposed method minimizes the energy export. Similarly, all these graphs are investigated for 10% of LPSP. It means out of 365 days, 10%, maybe for 36 days, my renewable energy system may fail to supply the demand or may fail to meet the demand of that building, just 10%. Then the graphs are shown here. In this scenario also, the proposed procedure has lesser energy export and import when compared to the previous conventional methods. Right? Similarly, this is the energy trend for the 10% LPSP, or LPSP is equal to 1. Right? And for zero LPSP, this is the result given by the algorithm. PV capacity is 28.7 kilowatt, 3.8 kilowatt of wind turbine, 854 kilowatt hour of battery. Put together, we end up with 33,794 US dollar. The total cost of the system achieved through the proposed method is 33,794 US dollar. But the cost of the system designed by the conventional method is just 7,600. Just 7,683 US dollar. This is almost 3-4 times greater than the the conventional method. Cost of the proposed method is 3 times or 4 times greater than the conventional method. If you see this particular table, we may get an idea that the conventional two objective function sizing technique is best or better in terms of annualized cost. But you come down to the last row of the slide, we have a factor called the total energy transfer index, which is just 0.15 for the proposed method, whereas for the conventional two objective function sizing technique, the total energy transfer index is almost 0.57, almost 0.6, 60%. So from this you can understand, even though we incur loss in terms of money, the system is so robust and grid so that it can minimize the total energy transfer index. See, I want to be I want to make it so clear. Even though the system end up with the maximum cost, the total energy transfer has been reduced drastically using the three objective function sizing technique. And the cost is very high because both procedure tries to attain 100% reliability. Both procedure tries to attain 100% reliability. So we have a very drastic change in the cost. So only if we care about the monetary analysis in terms of economic analysis, then definitely the proposed three objective function sizing technique is not acceptable if we expect 100% reliability. Definitely the conventional method is fine, right? Because we save 3 times of the cost, 3 or 4 times of the cost. But for 1%, for 0.1% LPSP, sorry, 10%, sorry, this is 10% LPSP, not the 0.1, right? It is just 0.1 or 10%. That is my typo error. For LPSP of 10%, or it should be simply 0.1. It is not 0.1%. So 10% of LPSP. If a system can afford 10% of LPSP, see, can we assure that we will get power from the EV 24/7 for the entire year? No way, right? We will definitely have some power cut due to maintenance and other things. So it is not practically feasible to expect 100% reliability. For example, if we can afford 10% power supply loss out of 365 days, maybe for 10% of our, we may be able to get power from the grid. Right here, the loss of power supply in the sense, building will not be in dark mode. Building will get power from the grid. Remaining 90% of the time, building will have its power from its own power generation. This is what I want to convey. Right? Loss of power supply probability, if it is considered as 10%, it does not mean that the building does not get power. During that 10% of the time, building gets power from the grid. Remaining 90% of the time, the building gets power from its own generation. If you understand this, you can understand this particular one. If it is 0% LPSP for the entire year, 365 days, the battery, PV, wind, this 3 component is more than enough to supply the building. It does not import even 1 unit of energy from the grid. If such a condition prevails, we can say that the system is 100% reliable, or we can say that the loss of power supply probability is 0%. Right. So, if you note down the result of this particular table with the 10% of loss of power supply probability allowed, you can note down the cost. The proposed method has $4,419. The conventional method has $4,051, which both are almost equal, just $350 extra. But now, come down to the last row, the total energy transfer index is just 0.14 for the proposed methodology. which means the unwanted energy transfer, unwanted energy export and import, we call it as energy transfer, that has been minimized, almost half of the conventional method system sizing, which results in 0.3. Here it is just 0.1. Similarly, you look at the other factor, grid interaction index, it is just 0.13. The system interacts with the grid, I mean, in exporting energy or importing energy from the grid. It is just 0.13 for the proposed method, whereas it is 0.21 for the conventional method. So if we allow, or if we can afford a minimum loss of power supply probability, the proposed method outperforms all other conventional method in terms of cost, TETA, grid interaction index, in all other crucial parameters. Right? These are all the other graphs shown for 100% reliability and 90% reliability. You can see here the energy export, the pink color line where I am dragging my mouse. This is the energy export by the proposed method. The dark red color line, where I am dragging mouse now, it is the energy export resulted by the two objective function sizing technique. You can see the energy export by the proposed method and the conventional method. Conventional method has energy export greater than the proposed method in all the month of a particular year, January, February, up to December. Every month, the proposed method has lesser energy import than the conventional method. Similarly, the next graph also confirms the superiority of proposed methodology. And here, this also shows the value of values of different parameter taken from both the methods for the lowest TETA value it has produced. It means that the proposed three objective function sizing technique has resulted lowest TETA value as 0.05, whereas the two objective function sizing technique has resulted 0.27 as the lowest TETA, right? And you can analyze all other parameters here, not the cost, because we are analyzing the lowest TETA, which means almost 100% reliability. For 100% reliability, our system will cost more. So that is also very evident here, right? And on the other graph, which is more important, you can see here, you see the purple line, which is the annualized cost of the system, right? And you see the green color line, which is the annualized cost of the system resulted by the conventional method. This purple line is the cost resulted by the proposed method. As we have discussed already, with zero LPSP, the cost of the proposed sizing technique is very much higher than the cost of the conventional method. You can see the difference. Green color point is here, purple point is here. So there is a huge difference in the cost. But as we gradually start to accept minimum loss of power supply probability, if the building owner accepts to get energy from the grid for a minimum period of time, you can see the drastic changes in the cost. As we allow or as we afford some amount of loss of power supply probability, you can see the drastic changes in the cost of the system. When you come to 6% of LPSP, you see very minimum difference between the cost of two different procedures, proposed procedure and the conventional procedure. As you go further, maybe at 8% LPSP or 9% LPSP, you can see cost of both the method becomes almost the same. cost of both the method becomes almost the same. It is equal. But look at the total energy transfer. You see the orange bar, which is the total energy transfer index, which is around the 0.15. But you look at the total energy transfer index of the conventional method, which is around 0.3. This is 0.15 and this is 0.3, double. Now, the cost is almost the same. If you follow my procedure, you will end up with the same cost as per the conventional procedure. But my sizing technique will result in half of the energy transfer. If my system have total energy transfer as 10 megawatt hour, the other system will have energy transfer as 20 megawatt hour. So now you can understand which system is grid friendly, which system has minimum grid burden, right? Obviously the proposed method, right? So from this we can come to a conclusion by choosing the third objective function, which is total energy transfer index, right? By choosing that as one of the objective function, the unwanted energy transfer, total energy transfer can be considerably reduced. That will help us to have or to design a grid-friendly net zero energy building, right? You understand both procedures are giving us the zero energy building, net zero energy building. The proposed method and as well as the conventional method, both will give us the net zero energy building result. But when you analyze the result, we can understand the proposed method will give us minimum total energy transfer, but the other method will give us a system which will have higher unwanted energy transfer between the grid and the building. So, and among them, if you have 100%, if you want 100% reliability, then you have to incur more cost. Very obvious, but it is noteworthy. Beyond a certain value of LPSP, if the owner can afford 10% of LPSP, let us say, the cost becomes almost the same for both the sizing technique. At the same time, the total energy transfer index value obtained by the conventional method is always higher than the proposed sizing technique for any LPSP value. Beyond this 10% LPSP or any LPSP value, the TETA is not beyond 10% or any TETA value, right? Any LPSP value, the TETA value is always lesser for the proposed method than the other method one. So in this context, so the proposed sizing technique will have lesser total energy transfer, which results in reduced grid burden, less transmission, lossless, and improved grid stability. But how this will contribute to the sustainability? That will be a question for many of the participants. See, when we design a net zero energy building with less grid burden and less grid interaction, then many such net zero energy building can be integrated with the system. If this integration of net zero energy building is disturbing the existing infrastructure, then we may not be able to interconnect more renewable energy system. If more renewable energy sources are not allowed, then definitely we have to rely on the conventional energy resources. Then obviously the CO2 emissions and all other environmental problems related to central energy generation system will be maintained for the years to come. So only if we design the system very optimally, and at the same time, you can integrate the PV, wind, anything to the grid. But whether the grid is able to withstand all this variability provided by the PV, wind, and all other renewable system, that has to be checked. Now, by the procedure, by the adopted procedure, you can see here, grid interaction index, one last figure, GII, grid interaction index. It is just 0.09 because the system merely interacts with the grid. Most of the time, it has its own sustainable power generation, energy generation. It hardly interacts with the grid. It hardly imports power from the grid. It hardly exports power to the grid. So, because of this building, the impact on the grid is negligible. Whereas the other result you can see, this is 0.25, 0.21. The grid interaction is 0.21. You see the other results. Here the interaction is 0.30. Right? You see here the interaction is 0.57. It means that almost 50% of the time the building is exporting energy to the grid and importing energy from the grid. Right? So then such type of buildings will be disconnected from the grid at one point of time if the grid is not able to maintain its stability, or if the grid is not able to maintain its balance between the generation and the demand. So with this, I will try to conclude my session as the time approaches near to the end at 7:15. And see, the work is really big due to the constraint in the lecture time of 1 hour 30 minutes. I restricted my presentation and results to the very important and the crucial thing. But if if the participants, researchers, and faculty members are really interested in net zero energy building related research work, then all explanations, very detailed explanation, every definition for the symbols, formula, everything is available in this particular literature. So you can refer this particular paper to get additional details of my presentation. So these are my references, my major references. So now I conclude my session. I'll be happy to answer if any of the participants or faculty members are having any doubt in the slides. Contribution of that work is finding that or introducing that the third objective. That the third objective function is a newly formulated or coined parameter which is not available or which was not used by any other optimization method so far in the literature. So to emphasize the importance of that particular objective function, we compared with the two objective function sizing technique. So if you add this parameter for optimization, then results will be better. So I cannot compare with some other third objective function, which may deviate the entire comparison. So either we have to compare three objective functions, same three objective function, or without the third objective function. Since this third objective function is introduced in this paper, I have no other paper to compare. So we compared with the two objective functions sizing technique. So this shows the importance of this paper. So it means that while optimally designing the system, this parameter, apart from the cost and the LPSP, this parameter also should be considered for minimization. So we will get the grid-friendly net zero energy building. That is the final inference or final conclusion of the work. Thank you.